Welcome to all. I am Dr. Santhosh Singh, working as Assistant Professor in Department of Physics. Today I am going to deliver ELRB on the topic Introduction of Nuclear Materials. So in this video lecture, I will cover the topic Importance of Nuclear Energy, Types of Nuclear Energy, Structure of Nucleus, Mass Energy and Nuclear Binding Energy, and next fission reactions. So let's start the topic. So what is the importance of nuclear material or nuclear energy? Basically, nuclear energy is generated through nuclear materials. So if we know the importance of nuclear energy, we can know the importance of nuclear material. Why? Because nuclear energy is generated through the nuclear material. So whatever the importance of nuclear energy, it's same as the importance of nuclear material. So nowadays, whole worlds are rushes for clean energy. So nuclear energy is one of the fundamental sources of clean energy. Why? Because it produce minimum carbon dioxide like gases and generate a maximum powers. So here it is written, the nuclear power debate is a long running controversy about the risks and benefits of using nuclear reactors or power to generate electricity for civilian purpose. When you hear the words clean energy, what comes to mind? So the first thing nowadays, it is every people are thinking about solar power energies and other wind turbines energy, but nuclear energy is also a fundamental source of clean energy. We will see in next slide how it is have a more benefit over all other sources of clean energy like wind source energy or solar power energy. And here I want to clear this thing. When you heard nuclear energy, people are often thinking about nuclear weapons. So nuclear weapons is another thing and nuclear power is another thing. Nuclear power is utilized for civilian purpose. With use of nuclear power, we can generate electricity, but nuclear weapons is different thing. It is used in war for destructions, massive destruction. So it is not our concern. We have a concern over only nuclear powers. So importance of nuclear energy. What is importance of nuclear energy? With the help of this chart, you can see that with the help of nuclear power, you can generate only 12 gram carbon dioxide like gases emission for per kilowatt power generations. Here you can see life cycle emissions of carbon dioxide gases equivalent per kilowatt power generations, per kilowatt hours power generation. So if you use the coal for generation of electricity, how much carbon dioxide like gases will generate for generating the 1 kilowatt hours power? 820 gram carbon dioxide like gases will emerge. But if you see, if you use the nuclear sources, what happens? It is only 12 gram carbon dioxide like gases will emerge. So you can, with the help of this chart, you can clearly tell that nuclear energy or nuclear power sources is the one of the best resource for generation of clean energy. Here from the chart, what there are other several wind onshore, wind offshore, tidal, hydropowers, concentrated solars, energy resources for generation of electricity. But over this, all these clean energy sources, nuclear power source also have some advantages over these resources. So it also keep the air clean by removing the thousands of tons of harmful air pollutants each year that contribute to acid rain, smog, lung cancer, and cardiovascular diseases. Generally, the carbon dioxide or carbon dioxide like gases, which is generally produced in generation of power. If you use coal energy, biomass energy, or natural gases or biomass dedicated gases, these type of gases will emerge, and it is responsible for lung cancer, cardiovascular diseases, acid rains. So if we use this nuclear power sources or nuclear energy, we can avoid the we can avoid the all these carbon dioxide oxide gases. How many? Thousands of tons of harmful air pollutants. We can avoid the emergence of thousands of tons of harmful air pollutants each year if we using the source, this nuclear energy sources. Obviously, this wind offshore or wind onshore also have a similar like character of nuclear energy, but this nuclear energy power source also have some advantage over these power sources. So we will see here. This is the also perspective of whole world where the nuclear power sources is used. So the first country who uses most nuclear power energy is United States. Russia, France, Ukraine, all the developed country, you can see this chart, all the developed country are using this nuclear power resources for generation of electricity. Our India is here. Now, only 1.6% of our whole power consumptions is generated by nuclear power plant or nuclear power energy. So we are too lagging behind from others developed country. Now in this slide, I am going to discuss nuclear energy advantages over other clean energy sources. So from this picture, you can see this is the platform for developing the solar power generations. So you can see here a large amount of land is required for generation of electricity with the help of solar power generation plant. But in the case of nuclear power generation plant, only this much land is required, and this source even eligible to contribute more power than this source. Means I want to say this much of land is required for solar power generation, but in comparison to this land, for nuclear power generation, we required only very less land in comparison to solar power generation, and we can produce more power than solar power generation. Okay, so this is the one advantage. And second one is, here you plant this solar panels. The industry where these panels are made is another one. So lot of transportation, and where the industry is located, where all these panels is made, it also requires some lands. So overall we can say that nuclear power plant required a less land comparison to others clean energy sources. Other clean energy sources means solar power plants or wind power plants. Wind, in case of wind turbine, we also required a huge amount of land, huge area of land for putting the wind turbines. So this is the one advantage. So it is clearly written here, despite producing massive amount of carbon-free power, nuclear energy produce more electricity on less land than any other clean sources. A typical 1000 megawatt nuclear facility in the United States need a little more than 1 square mile to operate. In comparison to this, wind farms require 360 times more than land area. To produce the same amount of electricity, and solar photovoltaic plants require 75 times more space. Means if you used a wind turbine, it required 360 times more land. And if you use solar panel for generating the electricity, it requires 75 times more land or space comparison to nuclear power energy. To put that in perspective, you would need more than 3 million solar panels to produce the same amount of power as a typical commercial reactor, or more than 430 wind turbine. Okay, so for generation of same amount of electricity which is generated by nuclear power plant, how much solar panel plant is required? 3 million solar panels. 3 million solar panels are 430 wind turbines. Okay. So that is one advantage of using nuclear energy. Now, the next advantage is, if you producing anything, then definitely after production of that thing, the waste material will be produced. So nuclear material are very dense material, and even a small amount of nuclear material, suppose 30 gram, I am giving just example, 30 gram uranium is sufficient for generation of 420 million electron volt energy. 30 gram uranium. Okay, and same power, for same power you can use too much solar panel, like previous slide I mentioned that 3 million solar panels are required for producing the same amount of energy. So 3 million solar panels, and these 3 million solar panels it is also have a lifetime. After that, after the lifetime of this solar panel, these are considered as a waste material. These panels are considered as a waste material. So you can imagine how much land is required for dump of these waste material. For dumping, how much land is required for dumping of these dense material. But in case of nuclear energy sources, a very small amount of nuclear material is required for producing the massive energy, so that the waste outcome is also very minimal. So here it is written that nuclear fuel is extremely dense. The amount of used nuclear fuel is not as big as you might think. However, some advanced reactor, nowadays some advanced reactor also came, and it is designed as so that they can utilize even waste material and produce the electricity. So all of the used nuclear fuel produced by the US nuclear energy industry over the last 60 years could fit on football field. Okay. So whatever the waste material came in last 60 years can be dumped in a one football field. So that is one advantage. Means you can manage your waste material within a small land. Okay. Now, what is the status of our country? How many nuclear power plant is working in India? Okay. So, whatever best of my knowledge, 8 nuclear power plant is currently running and generating the power. All are for civilian purpose, means it is only used for generation of electricity. Also, we have a nuclear weapon capacity, but these power plants are not anyhow connected to such program, means generation of nuclear warhead. These are purely for civilian purpose and generate the electricity for our India requirement. So what are the name? It is mentioned here. Tarapur Atomic Power Station. Its short name is TAPS. Some person telling Tapas. Okay. It is located in Maharashtra. The second one is Rajasthan Atomic Power Station. RAPS, Rajasthan. The third one is Madras Atomic Power Station, Tamil Nadu. The next one is Kaiga Generating Station. That is short name is KGS. It is located in Karnataka. In Tamil Nadu, the one another which is also having a largest capacity of nuclear power generation in India, and it is Kudankulam Nuclear Power Station. Kudankulam Nuclear Power Station, that is KKNPS. Okay. And one another is Narora Atomic Power Station. It is located in Uttar Pradesh. The another one is Kakrapar Atomic Power Station. It is located in Gujarat. And last one is Kaiga Generation Station. It is located in Karnataka. So 8 power stations, and they have several units. Okay. So approximately 22 to 23 units are there, and their capacity is also showing in this graph. Okay. So here, like TAPS means Tarapur Atomic Power Station, and 1, 2, 3, 4 means there's different units, and in another axis their generation capacity in megawatt is mentioned. Okay. Now, what is nuclear energy? I come on this topic. What is the nuclear energy? Okay. Before that, I was discussing what is the current status in India of nuclear power plant and what is the capacity of that power plants. Before that, I discussed what is the advantage of nuclear energy, okay, over other power sources, even over other clean energy sources. So now I will discuss what is the nuclear energy. So nuclear energy is a form of energy which is generated through three types of reactions. Reaction, this is not a chemical reaction, this is a physical reaction, means one highly kinetic energy neutrons, you know this thing, neutron denoted by N, react with fuel, nuclear fuel. Nuclear fuel means nuclear materials. Then one type of reaction will occur, and in that reaction a large amount of energy will produce. Okay. So this is the basic fundamental thing, so that we can tell how the nuclear energy will produce. And this process is called fission. Okay, fission reaction, where neutron and fuel will react. N stands for neutron, F stands for fuel. Okay, so what is nuclear energy? Nuclear energy is a kind of energy. It generates power through fission, and radioisotopic energy. Okay, fission means when one big nuclei will divided into lighter nuclei. One big nuclei divided into lighter nuclei. Then due to this division, a large amount of energy will release. Okay. So this type of phenomena is known by fission reaction. And what is fusion? Fusion means two smaller nuclei collide and create a smaller nuclei collide and create a big nuclei. So, and in this reaction also a large amount of energy will release, and this type of reaction, nuclear reaction, is called fusion reaction. The next thing is radioisotopic energy, means there are several radioisotopes. I am not going to tell what is isotope. So if we found the isotope of radioactive material, so these isotopes can also have a capacity to generate energy, and that energy also comes under nuclear energy. Why such type this radioisotopic component can generate energy? Why? Because they continuously decay to achieve their ground state, and in these decay processes there are lot of amount of energy will release. So there are three type of reaction, physical reaction, which is responsible for generation of kind of energy, that is fission, fusion and radioisotopes. And all the energy which drawn by these processes are known as a nuclear energy. Okay. So here I am clearly written. I clearly written here. Fission is the process of splitting a uranium atom. Uranium is a nuclear fuel or nuclear material. Okay. So if we split the uranium atom due to any means, the means is bombardment of neutrons on high energy neutrons on a uranium atom. So that uranium will split into smaller atom, krypton and beryllium. Okay, in that process, the huge amount of energy will release. So this phenomena is known as fission, and the energy which is released is known as nuclear energy. The same thing happens for fusion, and where the atoms are involved for generation of energy, all the energy comes under nuclear energy. Now, according to Nuclear Energy Institute, NEI, United States, that more than 476 million metric ton of carbon dioxide emission in 2019. Actually, this statement shows the advantages of nuclear energy nowadays. So I referred that data, I got that data, so I referred here. One agency working in USA, that is Nuclear Energy Institute. From Nuclear Energy Institute data, it is stated that the United States of America avoided more than 476 million metric tons of carbon dioxide emission in 2019. You can imagine the capacity of nuclear energy. Okay. That's the equivalent of removing the 100 million cars from the road and more than all other clean energy source combined. Okay. So all these statements confer the importance of nuclear energy. Okay. How it is important. So earlier I told that there are three type of process: nuclear fission, fusion, and radioisotope reaction are the physical process, and in this physical process the energy is released. Okay, so that energy is called as a nuclear energy. So I am going to tell here in briefly how nuclear fission energy work, fusion energy work, and radioisotopic energy work. So I already told that fission is what? Splitting of one bigger nuclei into lighter nuclei. One big nuclei splitted in lighter nuclei. Two lighter nuclei. In that process, a lot of amount of energy is released. Okay. And that energy is utilized for rotation of turbine. Okay. Here the one nuclear power plant symbolic representation where this fission reactor is there. Actually, there are two type of fission reaction: controlled and uncontrolled. So controlled fission reactor is here, and with the help of this fission reactor, energy is generated. That energy is used for heating the water, and after heating the water the steam will come, and that steam will responsible for rotation of turbine, and if turbine rotate, the electricity will generate. Okay, so nuclear fission energy, due to fission is what? Splitting of one big nuclei into two lighter nuclei. So, what is nuclear fission energy? The essence of nuclear fission energy is that the heat produced by the splitting of heavy radioactive atoms during the chain reaction is used to generate a steam or other process fluid that helps rotate the steam turbine generator, thus produce electricity. Okay. So the same thing I already elaborated, means whatever the energy released during the fission process, that energy is utilized by nuclear power plant to generate the electricity. How they utilize? There are big boiler. Boiler means where the water is stored. With the help of that energy, that water is become hot and steam will generate, and that steam will responsible for motion of turbine, rotation of turbine. Okay. So this is the nuclear fission energy process. Now I am going for nuclear fusion energy. Actually, in comparison to fission energy, fusion energy process, more amount of energy will release, and even in uncontrolled manner. So even people are trying to work, many scientists are trying to work the control this fusion process in a controlled manner, so that they can utilize this energy which is released in fusion process, and utilize after utilization of this energy we can also generate our electricity or whatever the requirement. But till now, the best of my knowledge, no control fusion reactor exists in the world. Okay, but yes, it is the fusion can occur, and in this fusion energy reaction process, the large amount of energy will release. So the same thing is written here. A huge amount of energy, much higher than fission, can be produced using the nuclear fusion reaction. Nuclear fusion reaction, deuterium tritium reaction. Deuterium tritium reaction. There is currently no commercial fusion reactor and is not envisioned to be set up for many years. A prototype, not working condition, a prototype fusion reactor known as a ITER, means International Thermonuclear Experimental Reactor, is being built in France. Work is going on in France. It is one information available in internet. Okay, the France is trying to develop the control fusion reactor. So what happened in fusion? You can see here, that is deuterium atom, lighter nuclei, tritium atom, lighter nuclei collide, and then again split in helium and one neutron. Okay, two lighter nuclei collides and responsible for generation of one different nuclei. In that process also energy is released. Okay, so when deuterium and tritium fuse together, their components are recombined to form a helium atom and fast neutron. As the two heavy isotopes are recombined into helium atoms and neutrons, the leftover extra mass is transferred into kinetic energy. This term is involved here, mass. So mass actually, okay, I will discuss it later. What happened in both fission or fusion? In fission, what happened? Lighter nuclei, one bigger nuclei is split into lighter nuclei. Okay, one bigger nuclei is split into, when neutron strike on one bigger nuclei, that bigger nuclei will split into two lighter nuclei, and in that process large amount of energy will released. Okay, but in comparison to fission, what happened? Two lighter nuclei collides and create one big nuclei comparison to this one big nuclei, and in this process also neutron plus energy, one big nuclei. What is the product? One big nuclei, one neutron, and energy will release. Okay, so both this energy is known as a nuclear energy. Why? Because it developed by nuclear process, some nuclear physics process. So this energy is referred as a nuclear energy, and with utilization of this energy we can generate electricity. The third one, and also important, radioisotopic energy. Okay, so actually this radioactive isotopic energy is generally used in remote space application, where we cannot perform any nuclear process in a controlled manner. Why? Because there are limitation of space also. If you are in space, definitely you are in a space shuttle, or might be if you are in international space station, then you have more space comparison to more space than a space shuttle. So whatever the space available there, you cannot perform fission or fusion reaction in a controlled manner. So, but energy is required there. So there, these type of radioactive isotopes is used. Although application of isotopes is very dangerous for health, but in some precautionary measurements we can utilize it. So how they can utilize and generate electricity? Either radioactive isotope plutonium, polonium, or 85 krypton, 90 strontium can produce a decay. They decay, actually they are radioactive substance. They decay to acquire his ground state, to acquire the stability. In that decay process, heat is generated. In all radioactive substances, if they decay, it is not necessary heat will generate, but in such type of radioactive materials or radioactive substances, or another name, the best name is fuel, ether. Such type of radioactive fuel, if they decay, they generate a heat. So with the help of that heat, we can, if we are able to utilize that heat in terms of power generation, then we can produce electricity with the radio, and that type of energy is known as a radioisotopic energy, and also it comes under nuclear energy. So this is the basic overview of nuclear energy. Now I am going to discuss in detail why these energy generated in fusion or fission process. So before understanding of these fission or fusion process, we have to know, we have the knowledge of, or we have to know the basic entity, that is atom. Means what is the structure of atom, and what is the masses of their constituents like proton, neutron, electrons, how they are located and all. Okay, so just for introduction of or just for overview of nucleus, for understanding of deeper understanding of all these fission or fusion reaction, I am going to give here an overview of nucleus. So atomic nucleus is the small dense region consisting of protons, neutrons at the center of an atom, discovered in 1911 by Ernest Rutherford, based on the 1909 experiment that is performed by Geiger and Marsden Goldfield experiment. That is performed by Geiger and Marsden, and it is very famous Goldfield experiment. Now, after the discovery of neutron in 1932, models for nucleus composed of protons and neutrons were quickly developed by Dmitri and Werner Heisenberg. Model means how the atom, how the electron, proton and neutron inside the atom are situated. So there are different models proposed by different persons. So one is the scientist Dmitri and another is Heisenberg. They proposed his model. That model elaborate about the situation or position of electron, proton, neutron inside the atom. So what he told? He suggested that an atom is composed of positively charged nucleus. Actually, we are very familiar with term atom. A unit of anything, whatever the word, everything is constituent with atom. The smallest building block of anything is atom. But atom is not a smallest building block. Even atom is made by electron, proton and neutron. So proton and neutron is situated at a center of the atom, and that center is collectively called nucleus. That center is collectively called nucleus. Okay, and around that center the electron is rotated as a like cloud. So another thing is electron is negatively charged, proton is positively charged, and neutron charge neutral. Means neutron don't have any charge. So what Dmitri and Heisenberg told, an atom is composed of positively charged nucleus with a cloud of negatively charged electrons surrounding it, bounded together by electrostatic force. Okay, so in nucleus there are positive charge electron, there are negative charge, and we know that Coulomb electrostatics rule. And what is the Coulomb electrostatics rules? The same like charges are attract each other and like charges are repel each other, and dislike charges are positive negative charges are attract each other. So here electron is negative charge, nucleus contain a proton which having a positive charge. So electron negative charge, proton positive charge, they attracted each other so that they can create a bound structure. They are bound together with the help of electrostatics attraction force. Electrostatics attraction force. Force of attraction. Electrostatics force of attraction. And they collectively called atoms. Okay. So almost all of the, and what they again told, almost all of the mass of atom is located at the nucleus. Nucleus. All the mass of atom, almost all the mass of atom is located at a center of the atom, means nucleus. With a very small contribution from the electron cloud. Means whatever the mass of atom, the most mass is contributed by nucleus of that atom, means proton and neutron. The contribution of electron is very less. Now these nucleus and these electrons are attracted by Coulomb force of attraction. Okay, but why these proton and neutron are bound together? So the reason behind that forces, reason behind the boundness, or what type of force is appeared there to get the bounded state of these proton and neutron at a nucleus is known as a nuclear force. That is a different type of forces, nuclear forces. It is a short range forces, and his amount is, that force amount is too much. It is greater than any other existence forces in the world, but it is a short range forces, means it is applicable for within the very short range distance. Okay, so that force are present there, and with the help of that force, that neutron and protons are bound together and form the nucleus. Okay, now that nucleus are bound with electron with the help of different force, and that force is Coulomb electrostatics attraction force. Why? Because they are dissimilar charges. Now, the another thing is, by performing the scattering experiment in which fast electrons are projectile that bombard target made of various elements, the size of nuclei of various elements have been accurately measured. This whole thing collectively called atom, where at the center the nucleus is situated, and around the center electron is surrounded as a, around the nucleus electron is surrounded as a cloud, negatively charged cloud. Okay, so this center part, radius of nucleus, means many scientists performed many experiments to determine the radius of nucleus. Okay, so by performing the Rutherford scattering experiment, this all gold foil experiment, which is written here, it is written somewhere. Gold foil experiment. This experiment also contributed in determining the radius of nucleus. Okay, so by performing the scattering experiment, the many scientists tried to determine the radius of nucleus, and what they found, they observed that any atom which atomic number is A have a radius R which is represented by R is equal to R0 a to the power 1 by 3. Means if they developed a formula R is equal to R0 a to the power 1 by 3, where R is the radius of that radius of nucleus of that atom. R0 is universal constant. A is atomic number of that atom which you want to find out the radius of that atom, radius of nucleus of that atom. So A is atomic number, R0 is constant. So value of R0 is what? 1.2 into 10 to the power minus 15. So 10 to the power 15 means 10 to the power minus 15 means Fermi. Means value of R0 is equal to 1.2 Fermi. Okay. So with the help of this formula, you can find out the radius of nucleus of any atom. Okay. The density of nuclear atom is approximately 2.3 into 10 to the power 7 kilogram per meter cube. How dense it is, you can imagine. Density of any nuclear. And one another thing, density of any nucleus is constant. Density. I am not talking about number of neutron and proton. Number of neutron and proton present per unit volume inside the nucleus is constant, irrespective of what type of atom and what is the atomic number of that atom. It is constant for carbon, nitrogen, helium, oxygen, whatever you have choose. It is constant, almost constant. Okay, so it is not in my concern, my topic concern. It is related to nuclear physics courses. Anyhow I remember this thing, so I tell this thing. So this density is very large compared to ordinary matter, example water, which is 10 to the power 3 kilogram per meter cube. Compare this 10 to the power 3 kilogram per meter cube, and this is 2.3 into 10 to the power 17 meter kilogram per meter cube. So how the dense is nucleus, you can imagine. Now I am going to tell about mass energy and nuclear binding energy. Why the energy is released in fission or fusion. Why the nuclear energy is released? Because loss of mass. If in both fission or fusion process, there are the constituent atoms lose his masses and they converted in different type of atoms. So if you calculate the mass of parent atom and product atom and compare, you find something is missing in mass, and that mass is converted in form of energy. Okay, so this mass energy equivalence is given by one of the famous scientist Albert Einstein. Okay, that is what he suggested. He suggested mass and energy is not equivalent. Any mass can be converted in form of energy, and how much energy they produce, if you want to know, you have to use this formula. E is equal to mc square. Means if any mass m can produce energy E, so what amount of energy is produced by that mass m is equal to what? Mc square. Okay. So the same thing is written here. Before the advent of theory of special relativity, it was pre-assumed that mass and energy were conserved separately in reaction. Before the introduction of special theory of relativity or before the Einstein hypothesis, of this mass energy equivalence, people are thinking that mass and energy both are conserved separately. Law of conservation of energy, you know. So, but before that, they also believed in law of conservation of masses. But after the Einstein investigation, where he investigated mass and energy are equivalence, means they can transfer from each other, then people are assuming that okay, only energy is conserved, not mass. So only one rule is hold, energy conservation rule, not mass conservation rule. Okay. So however, Einstein showed that mass is another form of energy and one can convert mass energy into other form of energy, say kinetic energy and vice versa. So Einstein gave the famous mass energy equivalence relation E is equal to mc square. Here the energy equivalent of mass is related by the above equation and c is the velocity of light in vacuum. What relation? E is equal to mc square means if you have a mass m, you can convert this mass into amount of energy E with the help of this formula, where c is the velocity of light. Velocity of light in vacuum, 3 into 10 to the power 8 meter per second. Okay. So all the things are important in understanding of nuclear fission reaction or fusion reaction. So now I am going to tell what is nuclear binding energy. Nuclear binding, the name itself confer that binding, the something who is bind these nuclear. Nuclear means I am talking about the central part of the atom, this thing. So what the energy which is involved to bind that nucleons, electron, proton, neutron. When I am telling nucleons, means I am talking about proton and neutrons. Nucleon. Why? Because they reside inside the nucleus. So collectively called nucleon. Proton, neutron collectively called nucleon. So what the energy? The whole nucleon together. That is nuclear binding energy. Okay. So I am going to tell this thing. So the atom consists of two parts, the nucleus which contain proton and neutrons and orbiting electrons. It is well known fact. Now, what is nuclear binding energy? It has been observed that when a nucleus is formed from its constituent particle, its mass is less than the sum of mass of the individual particles. Okay, what I am want to tell here means if nucleus means nucleon means proton and neutron. Okay, so suppose any nucleus having two proton and two neutron. Okay, so if I know the mass of one proton and mass of one neutron, if I know the mass of one proton and mass of one neutron, then we can know that mass of two proton and mass of two neutron. Add it. This same thing is present in this nucleus only. So whatever I am getting after adding, the same thing is mass of nucleus, but not. It is not happened like that. When you measured experimentally the mass of nucleus, you found that the mass of nucleus is little bit less comparison to the mass of their individual particles. Okay, so there are some mass defect phenomena, and that mass defect is stored in a form of energy which is known as a binding energy of nucleus. Okay, so the same thing is here written. So it has been observed that when a nucleus is formed from its constituent particle, its mass is less than the sum of the masses of the individual particles. The difference of mass delta m, also known as mass defect, gets converted into amount of energy with the help of Einstein's famous mass energy equivalence relation. This energy is known as the binding energy of the nucleus. Now I am going to discuss here in detail nuclear binding energy. For example, let us consider the case of oxygen atom nucleus. Oxygen atom nucleus case. Okay, I am considering here oxygen atom nucleus case, which has 8 neutron and 8 protons. So mass of 8 neutrons is, mass of 1 neutron is 1.00866 U. U is unified atomic mass. Unified atomic mass. Earlier it is AMU, atomic mass unit. Now it is converted. This unit is no longer exist. Now people are using U. It is Dalton or another name, unified atomic mass. Dalton or unified atomic mass. Okay. So we know the mass of 1 neutron, that is 1.00866. Okay. So mass of 8 neutron is multiplied 8 into this term. Now we also know the mass of 1 proton, that is 1.00727. Now mass of 8 proton is multiplied 8 into this term. So therefore expected mass of oxygen nucleus should be 16.12744 U. But what actually we get from mass spectroscopy experiment? There is one experimental setup known as mass spectroscopy. With the help of that experimental setup, we can determine the mass of atoms of any element. Mass of atom of any element with the help of mass spectroscopy experiment. So mass, but what actually we get from mass spectroscopy experiment? The oxygen atom mass is 15.99493 U. Oxygen atom mass, not nucleus. Now subtracting the mass of 8 electron. Why? Because oxygen atom also have 8 electrons. So if we want to calculate the mass of oxygen atom nucleus, we subtract the mass of 8 electron from this experimental value. So what we get? We get the experimental mass of oxygen nucleus to be 15.99053 U. Okay, this is experimental value. Somehow experimental value. Why? Because I don't have any experimental setup to direct measurement of mass of nucleus. So anyhow, we conclude that this is the experimental mass of oxygen atom nucleus. But this is experimental, this is expected mass of oxygen atom nucleus. So these two masses are not equal. Okay, these two masses, expected mass of oxygen atom nucleus and experimental mass of oxygen atom nucleus is not equal. There are some difference, and that difference is known as a mass defect. Thus we find that the mass of the nucleus is less than total mass of its constituents by 0.13691 U. The difference in mass of nucleus and its constituents, delta M, is called the mass defect. Delta M, mass defect. Mass defect. delta M, that is what? Z. Z means what? Atomic number. MP, mass of proton. Why? Whatever the number of proton is same as atomic number. So how many number of proton? Z and mass of one proton. Okay. So if you multiply it, then we get a total mass of proton which is present in any considered nucleus. So plus A minus Z Mn. A minus Z Mn means here the mass of neutron minus M, that is experimental mass. Experimental mass. Okay. Which is calculated by experiment. Calculated by experimental mass. Here A minus Z, A is what? Atomic weight. A is what? Atomic weight. Atomic weight. A. A minus Z is what they give? Number of neutron. Number of neutron. Number of neutron plus number of proton will give the atomic weight A. So if we subtract A minus Z, that will definitely give the number of neutron. Why? Because Z represents the number of proton. Okay. So what we get? A minus Z, number of neutron. Okay. So ZMP plus A minus ZMN minus M means mass of nucleon that is whole. That is mass of nucleon minus experimental mass of nucleus. Okay. That is this thing, the difference of mass of nucleon and experimental mass of nucleus is known as a mass defect, and it is denoted by delta M. So what is the binding energy? That mass defect converted in the form of binding energy, it is denoted by EV, and EV is equal to delta M multiplied by c square, velocity of light, square of velocity of light. The mass energy equivalence relation given by Einstein. So what is the binding energy? Delta M multiplied by c square. So it is the nucleus. Okay. So if we provide any nucleus the binding energy, that nucleus separated into their constituent particles. Okay. If we provide the binding energy of that nucleus will separate it in their constituent particles. So nuclear binding energy is the energy required to separate an atomic nucleus completely into its constituent protons and neutrons, are equivalent the energy that would be liberated by combining individual protons and neutrons into single nucleus. Okay. The same thing, you can reverse the order. There are separate nucleons, means protons and neutrons, and if you want to bound together and constituent one nucleus, you have to supply some binding energy. Okay. And if you supply this binding energy to this assembly, they will collide and create one nuclei. Now again, if you transfer this binding energy to this unified nucleus, then this unified nucleus will be split into their constituent particles. So that is the concept of binding energy. Okay. So on the concept of that binding energy, the fission reaction process will work. Fission reaction process. So what happens? We take in fission reaction, generally in fission reaction process, fission splitting of one big nuclei into lighter nuclei. So in fission reaction process, a fast moving neutron strike on uranium atoms, and this fast moving neutrons having enough energy which is required for break of this uranium atom, means it is this neutron having enough energy more than binding energy, so that this neutron break this uranium atom nucleus. Okay. So there are several reactions. You can ask the question here. Earlier you told that if nucleus break, it will breaks into their constituent atoms, means neutron and protons. But here, if when uranium atom breaks, it will breaks in beryllium atom and krypton atom. But this is the final product. Okay. Earlier it is breaks into neutron and proton, some neutrino, some different other type of particle will also generated, and they again recombine and build this beryllium and krypton atom. So this is not only two-stage phenomena, a lot of reaction in between them. Okay. So, but sake of convenience, I am giving here only this pictorial diagram. So one neutron strike on a uranium 235 atom, and they are responsible for break of this uranium 235 atom into beryllium 139 and krypton 95. And in this process, two neutron again generated, and also around 200 million electron volt energy is released. Okay. So same thing, neutron have enough energy more than the binding energy, so that when it's strike on uranium atom, the uranium atom will break in its constituent atom. And now again, after some large number of reactions, the final product is beryllium and krypton atom. Okay. So this is the fission reaction, example of fission reaction. And if you utilize this energy, 200 milli-electron volt, then you can generate the electricity with the utilization of this 200 mega electron volt energy. So the same thing is written here. When the nucleus of an atom splits into lighter nuclei through a nuclear reaction, the process is termed as a nuclear fission. This decay can be natural spontaneous splitting by radioactive decay, or can actually be simulated in lab by achieving necessary condition. Necessary condition means a lot of necessary condition. Even a binding energy more than binding energy is not only required factor. Even a lot of it is not a course of nuclear material. It is a concern of nuclear physics. A critical mass value means a certain amount of mass is required. It is not possible if you have a single atom and strike one neutron which have more energy than binding energy of that atom, so then atom will go for fission process. It is not happen like that. there are definitely, for fission reaction or fission process, they want some certain amount that is known as a critical mass, and it is not revealed by any country which have a nuclear all the country which have the nuclear power capacity, they are not revealing generally. It is very confidential thing, critical mass. So, but overall the same thing is happen, okay, for fission reaction. Now here it is written something, NF, neutron fuel reaction, that this thing, that is fuel, that is neutron. This thing is written here, neutron fuel reaction. So what is going during fission reaction process, it is written here. Generally, the natural uranium contains about 0.7% uranium-235 and 99.3% uranium-238, and trace amount very less, uranium-234 also. So if a neutron strike and the uranium atom will go for fission process, it is written here, carried out by fission fragments, while the rest by emitted neutrons, gamma rays, and eventual radioactive decay of fission products. The fission fragments rarely move more than 0.0127 nanometer. Yeah. Then again, this thing is happened. Actually, that is chain reaction. Whatever written here, I am going to elaborate all these things here. Here, uranium-235, that is fuel or nuclear material. Now one fast-moving neutron strike them, and it is splitted into 92 krypton and 141 beryllium, or 56 beryllium, 36 krypton. The whatever written here is atomic number. What is written here upper side is atomic weight. Okay. Now in this krypton, this beryllium generated and again generated approximately 2.5 neutrons. Here symbolically 3 neutron is given, and these neutron again responsible for doing same thing. Okay. Why? If you take an atom in a critical amount or critical mass as a nuclear fuel, critical mass nuclear fuel contains several millions of atoms. Here in pictorial diagram, only one atom perspective is given. Okay. So one neutron strike one uranium atom, and that uranium is splitted into krypton and beryllium. Okay. And generate 3 neutron. Okay. So forget about that krypton and beryllium. That krypton and beryllium is known as fission fragments. Consider these neutrons which is generated, and these neutrons is again responsible for same phenomena. Why? Because several uranium atoms is present. Okay, so during one strike, 200 around 200 MeV energy will produce. Now that neutron again strike with different atom. Okay, and they again strike. So you can imagine how much energy will release during fission process. Okay, each 200 MeV. So now again these neutron, so here you can imagine the same thing. So you can imagine that is the chain reaction. That's why fission chain reaction. And for performing this chain reaction in a controlled manner, it is very difficult. So that nuclear technology is little bit complex. Otherwise, they can able to produce a massive amount of energy, which can be utilized for mankind's. Okay. So all are the whatever I discussed here is I want to give some basic overview of nuclear physics and radioactivity, or whatever the phenomena involved in production of nuclear energy. My topic is nuclear materials. So, and process and all the process which is responsible for generation of nuclear power, means how we can make reactors and what type of material used in reactors, even some cooling process. So what type of material used for cooling process, and so on. What the structure should be of that nuclear reactor, so that we can utilize in more efficient and safer way. All the things will comes under this nuclear materials course. We will deal in all these things in our upcoming lectures. So this is the very first video lecture on the topic nuclear materials. Thank you for listening me. Thank you. Now here another things I forgot to mention. That is this is the symbolic representation of nuclear material substance or radioactive substance, not nuclear material, radioactive substance. So if you saw that picture, or if you will see that picture, you be sure that containers, if you saw this picture or any containers, be sure that containers contain any radioactive substance. So try to make a safer distance with that substance. Okay. So for awareness purpose, this symbols is used. Thank you. Thank you for listening me. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.